What is darkness? Well, a simple definition would be the absence of light, but certain materials can have a darkness all their own, can't they? An object that absorbed or otherwise trapped visible light would be very dark indeed. The more photons you trap, the blacker something gets. At least, that's how the blackest material on Earth does it.
Now entering the facility.
Unlike what I would usually do in a lab like this, use lasers to create light and such, today what I want to do is to create darkness. Thankfully, it's not all that hard to keep quanta in quarantine. Observe! A shoebox. Inside of this shoebox, I have taped a white piece of paper so that it's nice and bright and reflective, just like you'd expect. But I've also cut a hole in this shoebox. Now look at what happens when I close this very white shoebox. It is now jet black inside, even though you are looking directly at a white, very white piece of paper. Why is this happening? Well, light is still entering the shoebox through this hole, but it's bouncing around inside and not finding its way back out to your eye. So it's as though no light is coming from the box at all, and therefore it appears black. This is a very interesting little phenomenon, but we can do a lot better in terms of darkness than a shoebox. A lot better. Yeah. Light is very small. The flavor of visible radiation that you observe with your optic orbs is on the order of nanometers, or billionths of a meter. As a comparison, if you suddenly found yourself the size of a single grain of sand, which is rough and coarse and gets everywhere, light, at least visible light, would still be less than an inch long to you. So if you wanted to get on the same wavelength as light to trap it, then you would want to be on the nano scale. And that's exactly what the technology known as Vantablack does. Vantablack. Developed by Surrey Nanosystems, this Vantablack technology is actually an acronym for vertically aligned nanotube arrays. Vanta. These are little forests of carbon nanotubes standing straight up and very close together. In this orientation, Vantablack is exceedingly good at taking in light radiation but not letting it go back out, kind of like our shoebox, but to the extreme. It can absorb 99.9+% of visible light radiation coming into it. And because of this, when you apply Vantablack to a surface, the effect is phenomenal. It's replacing shadows and contours that you expect on three-dimensional objects and makes them look like two-dimensional objects, like it's pure void. But you can't buy pure Vantablack, and the gas depositing system at the facility isn't quite online yet. And I'm still on my quest for darkness. That's okay, because I got my hands on something else. Vantablack is a bizarre and surely awesome material, but like a lot of small-scale physics, it's really hard to visualize what the Vantablack is actually doing at those very small scales. But don't worry, I have one of these, a men's urinal splash guard that prevents drops of pee from getting everywhere.
That's nasty.
It's fine, it's just a demonstration. Think about how one of these actually works. When the colored water here falls on the urinal splash guard, it has some amount of energy. On structures not designed to trap the droplets, water gets everywhere as that energy takes those droplets and rebounds them. When the water encounters the guards with the vertical spokes, though, the majority of the droplet's energy is dissipated during those many collisions, and so it doesn't have the energy to ricochet back out and all over yourself. Almost the exact same thing happens with light in the carbon nanotube forests of Vantablack. Just replace the water here with photons of light and the lack of splash with the lack of reflection in Vantablack, and replace the carbon nanotubes themselves with plastic peepholes. And one more thing, this isn't really a conversation to have with other people in the bathroom. They're not interested, I find. This is Black 3.0, technically the blackest paint on the planet. It was created by an artist known as Stuart Semple and his many collaborators in an effort to spite the guy who bought the rights to the Vantablack paint and wouldn't share it with the artistic community. No, really, you can buy this paint online just like I did very easily, as long as you can prove that you're not that guy. Again, really. Now, I'm not totally sure on the chemical composition of this paint or the structure of it, but I do know that when it dries, if you apply it in the right way, the effect can be rather striking, like Vantablack at home. So I painted a number of objects for you, and I want to share the results with you now. Now, where were, oh, they're there.
He's been really excited to show you these, like, all day.
Of course I'm excited, my computing companion, because look at this quarter that I painted with Black 3.0. It looks like a glitch in the Matrix when I move it around. You're not getting any reflectivity, no depth. Even when I turn the quarter, it's hard to tell what it is. Ooh, oh, this is even better.
You don't even know how long he's been talking about this.
With a matte black paint that dries into some kind of analog of the nanoscale structures that make Vantablack so impressive, you can paint a playing card and make it look just unworldly, just like it's an absolute void. It looks like those black bars that TV editors put on screen when someone says something bad. Oh, wait. What the Black 3.0 absorbs up to 99% of incoming visible radiation, and I think there's an even better, more sciencey way to show you what this kind of stuff can do. Here I have the same painted objects on some nice white paper, and I'm gonna shine a laser on them using eye protection, of course. We will start with a standard 5 milliwatt green laser. The human eye is much more sensitive to green than red, so you should be able to see it all bright and lasery. So here's the green laser pointer, as you'd expect, nice and bright, but once it gets to the black, watch what happens. Wow, the physics involved here drastically reduce the reflected light. You can see even near the edge of the mask here, there should be reflection, should be what you expect, and then right when it encounters it, it's like a significant portion of the light just disappears into the void. How about something a bit more powerful? This is a big, scary laser that I own that is 200 times more powerful than anything you can buy off the shelf, and it's only legal here at the facility. Let's see how it interacts with our blacker than black objects. I hope it looks good because I'm not even gonna look at this. Here we go. Remember, I'm not even looking. Did I miss the quarter? I probably hit the quarter, didn't I? Nailed it. I also painted a mask with Black 3.0. Without the usual separation of light and the contrast that your brain is expecting to see, it is much, much harder to infer depth and orientation and all of that stuff. And look at me. Oh, riddle me dee.
I'm just going to go ahead and...
How about you? Vantablack and its analogs seem very high-tech, but as it often does, nature actually beat us to this kind of technology by a few million years. Observe the Gaboon pit viper. Objectively, the coolest snake, don't at me. It is. Not only does this viper have the longest fangs of any snake, not only does it deposit more venom per bite, and not only is it the chonkiest boy for its length, look at those scales. They can seem almost blacker than black. And that's because in 2013, scientists discovered that the scales that break up the snake's outline in the undergrowth have similar nanoscale structures as Vantablack, therefore achieving a similar effect. I guess you could call this color of black Viper Black, which sounds so much cooler. I don't have any Viper DNA. I have a question for you. We know that the blackest of black materials are very good at absorbing the light that we can see, but what about absorbing the light that we can't? In a moment, I'm gonna show you an image that I took of a relatively hot object that I painted some Black 3.0 on. My question for you is, will this splotch of paint be brighter, darker, or the same brightness in infrared light as this hot object? You take a second to think about it. I have some things I have to attend to. I'm on my way. Yeah, I'll be there in a moment. Separating the high-energy physics lab from the biosciences wing was a great idea. What does Field Scout Henderson even know about neutron activation and how it interacts with biology? Nothing, that's what. Nothing. This is really affecting our timeline. Sorry, I had to make something abundantly clear to someone. Now back to our question. What do you think we will see when we look at the blackest black with a thermal camera? Well, let's take a look. Okay, so the painted object that we are going to be using is just a teapot with some hot water in it. We want to be using something relatively hot because we need a large temperature to suss out all the little temperature differences. So if we look at the teapot, short and stout, and you can see that it is quite hot relative to the surroundings and relative to me. And if you look closely, you can even see my heat reflection in the metal of the teapot. Now, what do you think will happen when we turn this around and we see our dab of black 3.0? Well, let's find out. Okay, this is our dab of black 3.0. As you can see, it is much hotter than my hand, it's hotter than the surroundings, it's hotter than the metal of the teapot. Why is this the case? Well, it's because our paint is acting like what physicists call a black body, an object or system that can almost perfectly absorb incoming radiation and then radiate it back out according to its temperature. Stars are near perfect black bodies, for example, and black body radiation gives them their colors. At room temperature here, and with the temperature of this teapot being the same for both the teapot and the dab of paint is brighter because it can emit infrared radiation a lot better than the metal can. It has a better emissivity, as physicists call it. Interesting, isn't it? Thermal cameras. There can be so much more science than you think in just a little drop of paint. Radiation, emissivity, human perception, nanoscale structures. I think I found what I was looking for today. True darkness. And I hope that you did too. Until next time, not wearing a watch. Aria, can you just turn the lights off? Sweet.
Now exiting the facility.
Thank you so much to the facility's very nerdy faculty for being the main source of revenue for creating these videos and directly supporting them. This time, I want to thank Research Assistant Lee Elliott and Visiting Scholar Peter Hendry. If you want to join the facility, especially our Discord and our Patreon, where right now literally hundreds of nerds are talking with each other, sharing what they know, and memeing my face, you can go to patreon.com/Kyle Hill, or you can go to the link in the description of this video. And if you support the facility just enough, you can get your name on Aria here. And there's a lot of you, so I'm just gonna dance for a second. Oh, there's more of you this time. Science videos today for a nerdier tomorrow.